Okay, this is chapter 4, which is chemical bonds. So, when we're talking about bonding, remember bonding is going to be connecting things together. Much like bonding between humans is connecting humans together, right? So when we're bonding atoms, that's going to be connections between the atoms where they share something, in which case usually that we're talking about covalent bonding, which is going to be sharing electrons that are in those valence shells, the outer electrons of those atoms. So carbon, for example, is a great example of bonding because it has a wide variety of different types of bonding. So carbon commonly exists as something like soot. This is loose carbon, very small clusters of atoms, or even individual carbon atoms. And so soot, of course, is that ash that you see that develops, that black ash that develops on surfaces when they've been exposed to a fire. And when soot is subjected to high temperatures and pressure, you can start forming things like diamond. Diamond is going to be a form of carbon where you have a large number of carbon atoms that have formed covalent bonds in between them. And it makes a very nice little network. And that's what makes it so hard. So this process can be explained by understanding your chemical bonds that hold the atoms together. That's going to help you understand the difference between things like soot, graphite, and diamond. All of which are carbon, but are carbon in different arrangements. So one of the facts that you need to know for this is noble gases, such as helium, neon, and argon, are considered inert. And what that means is that they undergo few, if any, chemical reactions. And so they essentially don't make bonds. They don't make compounds. They don't react. So the theory is the inertness of these noble gases results from their electron structures. Each, except for helium, has what is referred to as an octet of electrons in its outermost shell. The easy way to sort of think about this is each row or period on the periodic table has its own shell. That's actually what the number is referring to. It's referring to what is referred to as a shell or energy level. And so once you've completely filled up a period, that means you've completely filled up the shell with electrons. And so a noble gas, which is at the end of the period, the last one in the shell, is going to be completely full shell. To fit any more electrons in there would require you to make a new shell. And you may remember the sort of example I used with electron configurations, and that was where you had the floors, the energy levels or shells would be like the floors of a building. And then the rooms would be like your electron configuration blocks. That was the s, p, d orbitals. Those were like the rooms in a building. And then the specific desks would be your location within that. Okay? And that was the final numbering where we started filling those in. Those were the specific orbitals. Okay, so when you're talking about an electron shell being full, it's a bit like filling up a floor on a building, okay? And so the next place you'd have to put an electron would be, well, it'd be the next floor, right? And you'd have to go up to a whole new floor, and, people might go, it's too much energy, too much effort, I'm not going to bother. On the other hand, if you have less than the floor full, you have a position. So if people want to fill in that floor, like there's a party going on, then there's a place for them to go. And so, for example, if there's a blank spot in that shell, if it's not full, then it's typically going to be reactive because it will want to gain electrons or lose them so it can drop down to the next floor or the next energy level. So the deduction that you can take from this fact, remember, parts of this course are to try to help you build up your critical thinking skills. So this is the sort of thought process that I want you to be able to do on your own. So one of the deductions you could take from this is that elements become less reactive when they alter their electron structures to that of a noble gas. So the more noble gas-like it is, the less reactive it will be. If, say, fluorine gains an electron, so it's a noble gas-like configuration, you would expect that negatively charged fluorine to be less reactive. And that is actually true if you're curious. So sodium here, this can lose one valence electron. After doing so, its core electrons are then going to be configured like the noble gas neon. And so right here's a sodium. It only has one electron in this higher shell. See this outer shell. If it loses that electron, it's then going to have the same electron configuration as a noble gas, as neon. It'll just have one more proton in its nucleus. And so you would expect, the theory we're working on here is that this would be less reactive than the sodium with the extra electron in it, right there. And that is actually true as well. Here's an example of a nonmetal, so chlorine. You would expect that chlorine would want one electron. And that's because it wants to have a noble gas-like configuration. And so here we see chlorine, it's one electron short of being like argon. Once it gains an electron in that spot right there, then it's going to be like argon. Keep in mind that these are not actually what atoms look like. Electrons don't just stay in place in perfect little orbitals, okay? They're just a nice visual representation. Okay, and so you would expect this Cl- with a -1 charge because it's gained an electron to be more stable, less reactive. So the Lewis electron dot symbols. G.N. Lewis developed a method of visually representing the valence electrons as dots around the symbol of an atom. And yes, that is G.N. Lewis, if you're curious. That's something that you don't get to see a lot, these actual scientists. All right, so these are Lewis dot symbols. Essentially what they are is they're the symbol of the element you're talking about, and then its valence electrons represented as dots. So for example, hydrogen has one valence electron, and so you put one dot to represent it. Noble gas, helium, has 2 electrons. You represent that with 2 dots. Neon has 8 electrons, a full octet. Octet means 8. And you put 8 dots to represent that. And fluorine has 7 electrons, represented here as 7 dots. You will notice that you actually fill these in by going 1 dot on each side, and then you start doubling them up, and finally they'll be full as an octet. Alright, so this right here is actually sodium reacting with chlorine gas. So here's sodium, which is a very shiny sort of silver metal. This sodium, interestingly enough, is somewhat dark looking, meaning it's actually starting to corrode. Oxygen's actually starting to react with it. You see these gas parts, that's actually the sodium metal. Chlorine is actually a greenish brownish gas, depending on how much chlorine gas you have. And you've actually probably seen chlorine gas if you've ever sprayed bleach on any rust or metal before. That would be chlorine gas. It's the horrible smell that you get. Please don't do that to try it out unless you are in a very well ventilated place, because that actually is poisonous. Okay, so if you put these together into a vessel to react them, they're going to react very vigorously. They'll release quite a bit of energy. This will actually burst into flames. As a side note, if you release this into water, sodium metal into water, if you have this powdered and you let enough moisture hit it, it's going to react violently anyways. Sodium metal is actually very reactive. Anyways. And finally, what you'll find is these solid white looking particles at the bottom of this, and that's actually sodium chloride, otherwise known as table salt. It's the salt you eat, when you put into food. All right, so this is the reaction of sodium reacting with chloride. Sodium wants to get rid of an electron. Chlorine wants to gain an electron. And so the sodium will give its electron to chlorine, giving a noble configuration for both of these. This right here is what's referred to as an ionic solid, and literally it exists because you have positive sodium ions that are going to be attracted to your negative chlorine ions, and they'll just repeatedly attract each other. So you'll have a sodium attracted to a chlorine, and then on the other side of that chlorine, another sodium will be attracted to it. On the other side of that, another chlorine will be attracted to it, and so on and so forth until you get this large crystal, or a bunch of small crystals. And this is what they look like. So sodium, chlorine, and you get the idea, hopefully. Of course, it keeps expanding out until you finally crack apart and start making a new crystal. And that right there is what's called a crystal lattice, by the way. Okay, so sodium and chlorine have opposite charges. Opposite charges attract. Positive sodium, negative chloride. And by the way, this is called chloride if you're curious. That's the name for the ion. Chlorine's the name for the gas. It's when it's not an ion. So this resulting attraction of repeated positive negative charges, this is what's referred to as ionic bonds. And so those are ionic bonds right there holding each of these together. Notice that unlike the covalent bonds we'll talk about, the ionic bonds don't have an actual anything in between per se. All they have is a positive charge being attracted to a negative charge. This right here is also an ionic bond. Any of these attractions between positive and negative are ionic bonds here. So these ionic compounds being held together by the ionic bonds, which are just the positive and negative attractions, these exist as what's called a crystal lattice. It's a crystal, as you can pretty clearly see. This is a salt crystal, just zoomed up really, really far, so you can see it nicely. And which, by the way, is the individual grains of the sodium chloride, the table salt. And the crystal lattice is the pattern, the motifs, if you're an art person, or patterns that exist repeatedly throughout this crystal structure. Okay, so these right here are some different types of metals and ions. You can see that many of them are very distinctly different. So for example, here we have calcium, metal, and here we have iron, metal. You can see there's a very distinct difference between these. These right here are a calcium ionic compound that you typically would eat a similar compound if you wanted to get calcium in your diet. This is actually how you typically get iron in your diet. You would eat iron ferrous sulfate, iron sulfate. And if it isn't in a pill form where it's greatly diluted, the crystals would look something like this. They are very distinct coloring. Iron compounds are usually very distinct coloring. Okay, so the octet rule. In chemical reactions, atoms tend to gain, lose, or share electrons so that they'll have 8 valence electrons. We call this rule the octet rule because octet means 8. Okay? And it's a very quick, easy to use rule. And it works for the majority of the mass in the known solar system, okay? Which means that it works really well for period 2. It's true for everything on period 2 all the time, okay? And that right there is the majority of the compounds you have to deal with on Earth. And so where it starts getting a little weird is period 1 only goes up to 2 electrons. So quote unquote, a full octet would only be 2 electrons, right? They want to be noble-like. I honestly do not like this octet rule. I think that people get caught up in the 8 electrons and that rule of it being 8 electrons when it could have so much easily been said, and as I've already said, everything wants to be like a noble, right? So everything wants to have a number of electrons like the nearest noble gas. There you go. And that will lead you to the octet rule when you need it. which is on period 2, where it is always true. So metals, which are on the left side of the periodic table, it's always easier to lose electrons, move to the left, to get to the nearest noble. And so metals will lose electrons to take on the electron structure of the previous noble gas and the previous energy level or period. When they do so, they're going to lose negative charge, meaning that they will become positive ions, which are called cations. One of the ways you can help yourself remember this is cations, cats are positive. So cations are positive ions. Nonmetals, which are on the right upper side of the periodic table, will tend to gain electrons. And that is so that they'll take on the electron configuration of the next nearest noble gas, which is to the right on the periodic table, where they're already very close to. And this means that they're going to typically gain electrons, and that means they're going to gain a negative charge, become a negative ion. Negative ions are referred to as anions. Anions, the easy way to remember that is ants are negative, anions. Alright, so these are some of the typical elements. The name of the ion, notice the names are for metals. Positive ions are always the name, hydrogen, lithium, sodium, etc. And then you just put ion at the end. For transition metals, it gets a little bit more complex. The stuff in the middle, in that D block, so the stuff in the very center towards the bottom, is what are called transition metals. Most transition metals have multiple charges they could be. And so when you talk about transition metal, you typically have to tell the charge it is. So for example, the copper with a 1+ charge that would lose 1 electron would be copper 1 ion, or cuprous ion, as you see right here. This is the common name, by the way. This is an old way of naming. The copper with a 2+ charge would be the copper 2 ion. And another way of calling that would be the cupric ion. By the way, iron actually comes, its names. So copper is Cu on the periodic table. That comes from cuprous, or cupric, or cupra, which is actually like, if I remember correctly, it's like a German fire god. That's where that gets named after. Iron 2 ion is ferrous ion, and that's actually the Fe that's on the periodic table for iron. That actually comes from ferric. Yeah, which again is another mythological reason. Essentially, they ran out of names for some of this stuff. Like iodine already was I, so they can't make that iron, right? So they ended up having to name things based on mythological beings. They ran out of stuff. What can I say? Alright, so a cation's charge. The charge of a cation from the representative elements is going to be the same typically as your family number. So the name of the cation is simply the name of the element with ion at the end. So this is the main group elements again. This is sodium, for example, is sodium ion. It has a +1 charge because it's in the first column on the periodic table. The columns, of course, being named the families. Alright, magnesium has a 2+ charge because it's on the second group or second family number on the periodic table. And it would be magnesium ion. You don't have to specify the charge because they're always the same as the group number. It's very easy to determine. Anions. The charge of an anion from the representative elements is equal to the family number -8. So the name of the anion is always going to have the root name of the element plus the suffix "ide." If you have a difficult time figuring out what the name would be, just try saying it. You won't be able to say it the incorrect way. The correct way will always be able to say it correctly. So for example, right here, this is family number 7, and so -8 would be -1 charge. Another way of thinking about this is it's one step to be a noble, and so it's a -1 charge. You gain 1 electron to be a noble. It is named chloride ion. It was chlorine, So you change "ine" to "ide," and you put ion at the end. This right here is oxygen. It will gain 2 electrons. It's 2 steps from being a noble. Or another way of saying that is it's in group 6, and so -8 would be -2. It is normally called oxygen. So you trade off the -igen part of it, the Y and beyond, and you replace that with "ide," and that will be the oxide ion. Notice, by the way, if you try to say it the other ways, it doesn't make sense in English. Oxide would not make sense, for example. To name binary ionic compounds, binary meaning 2 things put together, ionic compounds meaning as a metal and a nonmetal put together. You simply name the ions that are involved in the binary ionic compound. And that's because, again, they're just individual ions held together by positive and negative charges. So, for example, NaCl would be sodium chloride. MgO would be magnesium oxide. Notice again, metal comes first, followed by the anion. So you always put the cation followed by the anion. Many of the transition metals can exhibit more than one ionic charge, so when you name these, you always have to put Roman numerals, and these will denote the charge of those ions. So for example, if you have an iron with a 2+ charge, iron 2 ion. Iron with a 3+ charge, iron 3 ion, and so on. These are the commonly encountered ions that you would need to understand and be able to denote. Notice again, they're just based on the group numbers. I would not bother memorizing most of these things. I give you a periodic table anyways. Many non-metallic elements are going to react by sharing electrons rather than by gaining or losing electrons. So we had ionic bonding. Ionic bonding, a metal loses an electron to a nonmetal. That's the overall gist that we talked about. So now we're going to be talking about something where one thing isn't going to be able to lose electrons to the other. They're going to be too equal to do that. So they're going to have to share electrons. And this is called covalent bonding. So when 2 atoms share a pair of electrons, a covalent bond is formed. Atoms can share 1, 2, or 3 pairs of electrons. Sharing a single pair of electrons, which is 2 electrons, is called a single bond. Sharing 2 pairs of electrons, which would be 4 total electrons, would be a double bond. And sharing 3 pairs of electrons, which would be a total of 6 electrons, would be a triple bond. Notice, by the way, they have to share these electrons fairly equally. So this is typically going to happen between a nonmetal and another nonmetal. These are going to be 2 things that will both want to take electrons, and so they will share the electrons instead of one losing to the other. It can very rarely, and this is a much more advanced topic, happen with some of the metals that are on the lower right-hand side of the periodic table, okay? But if you want to learn more about that, send me a message. If not, don't worry about it. If you go on to any further chemistry, you can learn more about it. They make really interesting stuff, but you don't need to know for now. All right, so binary covalent compounds are going to be named using a prefix that denotes your number of atoms. So here's the prefixes that you'll need to understand and know. Mono is in monocole or monocycle. That's 1. Di, 2. Tri as in tricycle, 3. Tetra as in Tetris, 4 sides, that's the box you do Tetris in, is 4. Penta as in pentagon, 5. Hexa as in hexagon, 6. Hepta as in heptagon, 7. Now, honestly, Pentagon, most people remember Pentagon because it's a building that, the generals work out of in the United States. Hexagon, most people remember that, or they remember hex wrench, and so most people don't have difficulties with that. Ironically, hex, as in I put a hex on you, is also due to the 6-sided nature of the symbol for it. Hepta is the one that most people don't remember well. And I've used to give out a bounty for people to come up with ways of for you to remember these things. Somebody finally won it. It was a nursing student of mine in my previous semester. It's really funny. It's really memorable. But considering I'm a 30-something-year-old male, it will sound a little bit like sexual harassment. So I am sorry before I even say it. All right. So Hepta, the way she came up to remember this is 7 minutes in heaven, you get Hep. And of course, that being, you have sex and you can get Hep from the other person, like Hep C. So, anyways, Hepta is 7. Hopefully that helps you remember it. All right. Octa, as in octopus, is 8. That's in 8 atoms. Nona is 9. And again, I used to give out bounties for this, bonus points for this. Nana, the interesting one they came up with for this is the goddess for birth, back in, I forget if it's Roman or Greek culture, was named Nana. And that's where that comes from. Nana, 9. 9 months to give birth. So, kind of an interesting one. Deca is in decade. 10. So, binary covalent compounds have 2 names. The first name is the prefix plus the name of your first element. You do not need to name this one mono if it would be mono. You can just drop it. Okay? So if you only have one of the first element, you don't need to name any mono. You don't need to use a prefix. And notice that you don't need to change the ending, the suffix of that name. And I'll give you some examples in a bit. But first, let's understand the overall gist. The second name will be the prefix plus the root name of the second element plus a suffix, which is usually "ide." Okay? And this is much like the ions. When you do the ionic compounds, you put "ide" as the suffix for all those. Notice that the second name, you always put a prefix. Even if it be mono, it gets a prefix. So here's some different examples. We have here sulfur, and we don't put mono because there's only one. So sulfur, there's 4 of them, so tetra, bromide. Right here we have diphosphorus. This is wrong, so it's diphosphorus. There's 2 of them. And this is 3, so trioxide. Diphosphorus trioxide. An interesting point, by the way, this is one of those things that when people learn this, they sometimes decide to do a little bit of a practical joke, and it actually is really funny to do. So what it's called is the dihydrogen monoxide joke. So dihydrogen, 2 hydrogens, monoxide, 1 oxygen, that's water, H2O. And so the joke is you list off all the bad things about dihydrogen monoxide, water. By saying dihydrogen monoxide, you never let them know it's water. And then you try to get the person riled up like they're going to want to ban it. And this joke has been successfully played on such illustrious groups as the entirety of Facebook several times, repeatedly every few years. It's been played on major environmental groups. It's been played on the State Senate of Arizona. Somebody played this joke on the State Senate of Arizona and almost got water banned in Arizona. Arizona almost put money and banned water from their state. So, and here's sort of how you do it. For example, there's a 100% addiction rate to dihydrogen monoxide. Think about that for a second. Every human is addicted to drinking water. You can't survive without it. Dihydrogen monoxide kills more people than every other drug combined. Yeah, more people drown from dihydrogen monoxide, or water, than OD on any other drug, right? On all ODs combined. Dihydrogen monoxide causes more damage to property than every other cause on the planet. Well, of course, that's water damage, right? That's things like floods. That's things like hurricanes. That's most property damage is done by water. So when you start naming all the things about it, it sounds horrific, right? But if you knew what water is, you realize very quickly you can't live without it. So the most ironic one to me is last time one of my students did this. They did it on Facebook, and a group of my students, one of my students, their parents didn't talk to them for like a week because they were laughing about it, and their parents didn't bother looking up that it was H2O, water they were laughing about. Uh, I find the Facebook one hilarious because they could have just Googled it, right? Dihydrogen monoxide, Google it. Yeah, that's water. Anyways, so electronegativity. This is going to be a measure of an atom's attraction for the electrons in a bond. So the more electronegative something is, the more it's going to pull the electrons in that bond towards it. So for example, fluorine, if it's in a bond, is going to pull the electrons from the other stuff so that the electrons spend more time around it, and it's going to hog those electrons even though it's sharing. If you've ever shared anything with anyone in your life, then you can relate to this very easily. We've all gotten something we're supposed to be sharing, and then one person takes like 70% of it, right? And then you're left with 30% of it, and you're like, well, thanks. I'm glad we split that equally. Well, the same thing happens with atoms. So you see here that the electronegativities, they're going to increase as you go up and to the right. That means that fluorine, for example, is going to hog electrons whenever it gets into a bond with anything else. If this difference is very small, then they're going to share the electrons almost equally. For example, the difference between things like boron and hydrogen and carbon and hydrogen will share it almost equally. If you had two carbons, they're going to share it equally together, okay? And that'll be a covalent bond. No difference, that's just sharing all the electrons equally. If you get a big enough difference here, like a nonmetal with a metal, then one of them is going to take the electrons from the other. So for example, you have oxygen and potassium here. The oxygen is going to take the electron from the potassium, and that's actually what these electronegativities are showing you. What if you get something that has somewhat of a moderate difference, like carbon and oxygen? This is going to be called a polar covalent bond. And this is a bit like halfway in between an ionic and covalent bond, okay? So what you'll get is the carbon will end up with very little electron density around it. The oxygen will end up with most of the electron density around it. It's still going to share the electrons though. That's why it's called a covalent bond, a polar covalent bond. Is because they still share the electrons, just one typically has the electrons around it more than the other. All right, notice by the way that the electronegativities do not show up on the noble gases. Noble gases do not have electronegativity, and that's because they don't bond. And remember, it's how much it attracts the electrons in a bond. So it has to bond to do this. Please note also that hydrogen sort of bucks the curve. So hydrogen right here, your biggest steps in electronegativity are going to be going up and down the periodic table. So you see that these are usually whole unit differences when you're going up and down. Keep in mind these differences get smaller as you go further down the periodic table because the number gets smaller. But overall, your largest differences, like fluorine versus chlorine, it's a very large difference in electronegativity. And again, that's because we're going down to a new period, a new floor. Okay? As you go from left to right, right will have your larger electronegativities, but the differences are going to be relatively minor. They're not going to be the largest changes that you see. So when you go from left to right, you'll have increasing electronegativity, but the differences are going to be smaller than if you had gone up the periodic table, for example. By the way, this pattern is very easy to remember as long as you remember metal, non-metal. Okay? Non-metals are up and to the right. Electronegativities in non-metals are going to be higher, so the same pattern exists. As you go up and to the right, increasing electronegativity, things become non-metals. And they start taking electrons. As you go down and to the left, those are going to have lower electronegativities. That's the reason they lose electrons. That's the reason they're called metals. So this is a polar covalent bond. When you have two atoms that have differing electronegativities, and they form a bond, they'll make a covalent bond again, but they won't share the electrons equally. And so this is referred to as a polar covalent bond. Polar literally means it has poles like a magnet. And so the electrons will spend most of their time around the thing that's more electronegative, then that's going to have a partially negative charge. By the way, that's what that small delta symbol means. Partial negative. That's the negative. The thing that has a lower electronegativity is going to have less electron density around it, meaning it's going to be more positively charged. And so the hydrogen, for example, here is partially positively charged. Notice you have a positive and negative sides. That's like a magnet that has a north-south. In fact, that's what a magnet is. It has a positive and negative side. So the bond polarity, this can be represented on a Lewis structure with either the partial symbol or with an arrow. And so here we have this partial symbol, partial positive, partial negative that you're seeing. The arrow would be a positive sign on this side, and then you'd extend the positive sign to form an arrow towards the negative sign. And that would be positive, negative, much like the direction where your electrons are heading towards the negative side. The difference in electronegativities between the two bonded atoms can actually be used to determine that type of bond. That's actually what makes them a nonpolar covalent bond, which is a normal equally shared covalent bond, a polar covalent bond, or an ionic bond. Please note here that this is actually a sliding scale, okay? This has a continuum between them. So as you go larger and larger electronegativity differences, you'll be increasingly ionic in character. As you go less and less electronegativity difference, you'll be increasingly covalent in character. So if you have an electronegativity difference of less than 0.5, then you'll have a nonpolar covalent bond. If it's 0.5 to 2, that will be a polar covalent bond. And if it's greater than 2 in electronegativity difference, that would be ionic bond. So here's polyatomic ions. These are going to be groups of covalently bonded atoms with charges. So these right here are going to be covalently bonded atoms that together have a charge and form an ion, okay? And so they are polyatomic, many ions, atoms, ions. By the way, some of the important ones that you may want to know are things like acetate ion. This is actually what gives vinegar its flavor, is acetic acid / acetate ion. Right here we have nitrates, and those are what you see in like plant soil when you want to pot a plant. Nitrate content is very important when you want to grow crops. Cyanide ion, cyanide is in the poison cyanide that you probably heard of before, typically in the form of hydrogen cyanide. Anyways, these right here are the phosphates, by the way. Phosphates are actually what usually gives soda its preservative qualities. Permanganate ion is kind of an interesting one that you've probably never seen or heard of it before. It's an incredibly powerful, very reactant, very reactive. It can oxidize pretty much anything. Carbonate ion is what most rocks are, and it's also what your teeth are. And that's actually why if you drink an acidic drink, it actually causes the carbonate ion to go to CO2, and it literally destroys your teeth. Okay? Slowly but surely. Sulfate ion, this is in like sulfuric acid, but you've probably heard of and seen this before and not realized it. This is one that name-wise most of you have never heard of, but you've all seen before because it's usually at least part of different types of corrosion. Like some of the copper patinas you guys have seen, that sort of bluish color, those are oftentimes copper sulfides and copper sulfates. That's what makes that sort of wavy different colors to it. Anyways, when writing formulas for compounds containing polyatomic ions, it may be necessary to use parentheses to denote the proper number of ions. Okay, so right here's an example. We have a calcium ion and we have a nitrate ion. Now, notice that these formulas, the overall ionic compound, always has to have a charge of 0. And that's why it doesn't have a positive or negative charge up here. It doesn't have anything because it has an overall charge of 0. And what that means is your positive and negative charges have to equal out. So, that means that you can have one calcium, which is a 2 plus charge. You would have to have 2 nitrates to make up that 2 plus charge, or to neutralize the 2 plus charge. So how in the world do I represent NO3 happening twice? Well, a lot of people are going to make the mistake, and this is a very common mistake to make, please don't make it. They would try to put 2 here and 6 here. But that wouldn't be nitrate anymore, okay? That's like, instead of if I was to represent 2 humans, yeah, they have 2 arms, 2 legs, 2 heads, right? Or 4 arms, 4 legs, 2 heads all together. If I put all of that onto a single body, I'd be in trouble, wouldn't I? That would not be a human anymore. So, I have to represent that there are 2 individual humans. There are 2 individual nitrates. And how I do that is I put the nitrate, NO3, inside of parentheses, and then I put a 2 next to it as a subscript to say, hey, there are 2 of these NO3s. Please note that putting a 2 in front of here means something different. That means there are 2 calcium nitrates. Putting a 2 here would mean there are 2 calciums. So please pay attention. The devil is in the details. Much like if you were to say he or she, that would change a sentence considerably and may even be grounds for harassment depending on the situation. All right, so please pay attention. This is a language that I'm trying to teach you parts of, okay? So when naming compounds with polyatomic ions, simply name the ions in order. So here we have an example of the formula, and we're trying to come up with the name of it. So this is ammonium, if you look at your polyatomic ions, and then this would be sulfate. And so all we'd have to do is write that out, ammonium sulfate. There we go. Notice we don't have to name how many of them there are, because these are still binary ionic compounds. They just happen to have polyatomic ions. So here's the rules for sketching Lewis structures. Rule 1, you always count the valence electrons. So what we're going to do is we're going to figure out how do these connect. That's what a Lewis structure tells you. The first thing we need to figure out is the number of valence electrons. That's the same as the group number. So for example, you have a carbon, you're going to look for carbon and look at the group number. That'll be your number of valence electrons. 4. Second step is sketch a skeletal structure. So you'll put each things together with single bonds between. Step 3, place electrons as lone pairs around outer atoms to fulfill the octet rule. So you fill in the stuff that's on the outside, leaving the one in the center alone. Step 4, subtract the electrons used so far from the total number of valence electrons. Place any remaining electrons around the central atom. And so you fill in the stuff around it, you figure out how much you have left, and then you put those on the central atom. Step 5 is the central atom lacks an octet. You will then move lone pairs from an outer atom into double or even triple bonds to complete that octet on the central atom. Okay, now here's some examples of these that you can see. I'm actually going to post separate videos just to show you how to work them out, because it does not work well for me to try to do this on the PowerPoints. It just doesn't work out, okay? So an atom or molecule with an unpaired electron is going to be known as a free radical. And some examples of this are things like NO and NO2. Collectively, these are actually known as NOx, and those are actually the source of smog, if you're curious. And things like ClO2, which is a chlorate. Okay, so stop the video, look at my example problems where I teach you how to do the Lewis structures on those videos of me doing those Lewis structures, and learn those first. Because you need to figure out a Lewis structure before you can figure out anything else. If you're going to figure out the shape of something, first you need to know what part's connected to what, right? So now, once you come back, hopefully you know how to do a Lewis structure and you understand what they look like. The valence shell electron pair repulsion theory, which is VSEPR theory, is going to be what you use to predict the shape of molecules and polyatomic ions based on the repulsions of electron pairs on central atoms. It's actually much simpler than you'd think. So if you have two things that repel each other, remember, these atoms are going to have electrons around them, meaning they will repel each other. They will not want to share the same space typically. So if you have two things, 1, 2, around a center atom, to get as far away as possible, they're going to adopt a linear shape. And so what we call these is, I call them electron domains. Okay, that is the upper. That is the way that spectroscopists typically call them. That's the way I was taught to call them as a physical chemist. You'll see them called all sorts of things: electron clouds, electron sets. Overall, what they're talking about is the electrons in this bond here, the electrons that are associated here, they take up space, okay? And they're going to repel any other groups or domains of electrons that get close. And so what you do is you just count up your number of electron domains around your central atom, and then that's going to tell you what shape it will take, because they will want to try to get as far apart as possible. By the way, this is why I call this electron domains. A domain is an area that you take up and have control over, right? And so the electron domains, well, electrons don't want other electrons in their domains. So the electron domains always separate as much as possible. Here we see trigonal planar. It's going to be a triangle on one plane. That's going to be the maximum separation for 3 electron domains. This right here is tetrahedral. This is actually the maximum separation for 4 things. By the way, it takes up the same shape as a camera stand, a tripod for a camera. 3 legs, maximum separation to give you the most stable base you can get. And then finally a arm that's going to be the maximum separation from those to give it the best height you can get. There you go. Alright, so these right here are some different VSEPR shapes based on the number of electron domains. Now I talked about the number of electron domains so far, which would be this number right here. The book I took this from had this called electron sets. Okay. Now I haven't talked so far about the difference between bonding atoms and lone pairs. So the electrons in bonds are going to be different than the electrons that are in lone pairs. So bonded electrons are going to be this number right here. These are going to be electron domains that are bonds, that have an atom on the other side of that, like so, or like this. Lone pairs are going to be where you have an electron pair, electron domain, that doesn't have an atom on the other side. It's just a pair of electrons, no atom on the other side. And those will be lone pairs, as you learned in the Lewis structure portion, hopefully in the Lewis structure videos. Okay, now again, lone pairs are pairs of electrons that will be on this central atom that do not have an atom on the other side. They're not involved in a bond. Now, when we talk about the molecular shape, this is the shape of the molecule, meaning the shape that the atoms adopt. The electronic geometry would be these types of geometries, period. You don't have to worry about lone pairs at all. okay? Keep in mind when we look at this, the number of bonding domains versus the number of lone pair domains always has to add up to the total number of domains around your central atom. So when we are talking about this and they don't have any lone pairs, then whatever your geometry is, your electron geometry, it's going to be the same as your molecular geometry. There's not going to be any difference. We don't have to worry about a difference. So if there's no lone pairs, there's no difference. 4 different groups around it gives you tetrahedral, period. Don't have to worry about it. The difference is when you have a pair of lone pairs, that's going to mean that one of your groups doesn't have an atom at the end. So the molecular shape, the best analogy I can give you for this is when you sit down in your chair, it makes you have a bent shape, right? You're bending because you're sitting in the chair. However, we don't count the chair as part of you, do we? So we say that you have a bent shape. We don't say that you have a triangular shape, which would be the shape of you plus the chair, right? Well, lone pairs do a similar thing. They take up space, but they don't have an atom at the end. So you don't count them as part of the molecule shape. You just look at the atoms. So for example, in this case right here, we have 4 electron groups, 4 electron domains. And that would give us a tetrahedral shape normally, right? But notice that one of these would be a lone pair, the one on the top here. And so we just get the bottom part of that shape as our molecular shape. And so that's going to be called trigonal pyramidal. Notice it makes a little pyramid with a triangular base. Or here, again, 4 would mean it's tetrahedral, right? But 2 of those would be lone pairs. So think of 2 of these being gone. 1, 2, those are gone. They're lone pairs. We don't look at those anymore. So all we had left is this, this, this. That would be bent, like so. So again, they're being forced into that shape because of the lone pairs, but we don't want to look at the lone pairs. We're looking at what does the person look like, what does the molecule look like. And so this is bent. Okay. Hopefully that makes sense. Again, I have separate videos for these as well to help you out. So shapes and properties, polar versus nonpolar molecules. So in order for a molecule to be polar, 2 conditions must be met. You have to have polar bonds, which means a significant difference in electronegativity between the 2 atoms. The second condition is these bonds must be arranged such that the separation of charge exists, that you have an overall positive and an overall negative side to this molecule. And that's where the name comes from. Polar, meaning it has poles, molecule. Nonpolar, meaning it does not have poles, molecule. Right here is an example of something that does not have poles. So it has slightly positive hydrogens, but notice that they cancel out. You have slightly positive every direction, and they cancel out overall. So you have no overall poles. This is called a nonpolar molecule then. This right here, notice you have a negative side and a positive side. And so this is a polar molecule. And that's because it has individual bonds that are polar, and they line up to give you an overall negative and positive sides. Again, this is probably the single most famous polar molecule, which is water. And that's what makes it the universal solvent. That's what makes it the #1 greenhouse gas. You may not know that, huh? Water actually causes about 2/3 of the greenhouse effect, which is what we talk about when we talk about global warming, okay? If you're ever curious. All right, so let's talk a bit about green chemistry while we're at it. Through an understanding of chemical bonding, molecular geometries, and intermolecular forces, we can design and develop new medicines, molecules, and materials that benefit society, and at the same time, have minimal impact on the environment and human health. An interesting side note is this has been most of the development over the last 20 or so years, is really just making things more green, less toxic, less damaging to create. All right, so let's talk a bit about the vocabulary. We have a name for a compound, so like ammonia, that's the name of this compound. We have a chemical formula, which is this right here. That's your chemical formula then. It's a formula that tells you what the compound has for atoms. And this then would be your Lewis formula. And it's going to show you how things connect together. For example, the hydrogen is bonded to the nitrogen. This then is called the molecular geometry. And this is going to be the geometry that the atoms occupy in your molecule. Please note, by the way, as a reminder, if it has NH3 and a Lewis formula like so, this is the same compound. There's no difference between NH3 that comes out of a pig's butt and NH3 that comes out of a factory. Okay? They are the same. They are both ammonia. Pig's butt is probably the. By the way, ammonia is that thing. If you ever been to a pig farm or a poultry farm, that really sharp stinging sensation in your nose, that's ammonia. If you ever spray Windex, you'll get the same smell. And that's that sharp stinging sense in your nose. That's ammonia. Okay. Good luck, folks. Please let me know if you have any questions. This is very actually useful information on this one.